Okay, so here we go. Last lecture of the semester. Very exciting. We're gonna do a bunch of stuff today, and we can do this bunch of stuff because a huge amount of what's in chapter 4 is actually kind of review. It's if not review, it's kind of analogous, strongly connected to stuff that y'all have seen before in single variable calculus classes. First of all, let me just remind you what a Taylor polynomial is. Taylor polynomial, here's the general formula that I'm sure y'all recognize. But just a reminder, a perspective on why we would ever care about such a weird-looking construction is that this is the unique polynomial of degree k that agrees with f at the point A in terms of value, in terms of derivative, in terms of second derivative, third derivative, fourth derivative, et cetera, all the way out to kth derivative. So this, if you're looking for a polynomial that mimics your function, right? It's got all, it behaves just like your function f, at least at the point A, in terms of values and derivatives. This is the unique polynomial of degree k that will do that. Right? So, very nice. Now, what's the multivariable version of that? And, well, the target that we're going to aim for is morally equivalent. We're going to look for a polynomial that mimics f in terms of value at the point A, in terms of derivatives. Okay, we've got to be careful with this. We're in a multivariable context at this point. There's actually a bunch of different partial derivatives. I want all of the partial derivatives to be equal, right? I want this polynomial to mimic f in terms of all of its partial derivatives and all of its second partials, third partials, fourth partials, of which there are many, right? All the way up to and including all of the kth partials of at the point A. Right? So this is going to be our goal, is to find a polynomial that will do this. And there is, again, going to be a unique polynomial of degree k that does this. We're not going to talk about the full formula. It is in the book. It's kind of notation heavy. We're not going to really use anything beyond k equals 2. So let me show you what the answer is for k equals 2. This right here is the Taylor polynomial of degree 2 in the multivariable context. All right. So a couple things to notice about this. The first thing I'm going to notice is that if you look at the first two terms, those first two terms are literally the linear approximation. Right? It's flashbacks to chapter 2. It's just exactly the linear approximation. So really, when we say second order Taylor polynomial, we're really just saying in the same sense that this first order term is just an improvement over just f of a, right? Jumping to the second order Taylor polynomial just says, all right, what is the second order term that I have to add to keep the good thing going? Now the answer to that question, that's the other thing I wanted to point out. First of all, you're going to notice this is a quadratic form. So flashbacks to Math219, recall linear algebra comes up here and there in this course. This is one of those places. So remind yourself at some point of what are quadratic forms and how do you deal with them. Specifically, a quadratic form is in relation to a matrix, and the matrix here is this thing. It's called the Hessian matrix. And no big deal. It's just the matrix of all the second partials. That's it. Pretty easy to write down. So I think a really good exercise, and everybody should do this. You don't have to, but I strongly advise. You can check for yourself directly, plug and chug, that this function agrees with f in terms of value at the point A, in terms of all the partials at the point A, in terms of blah, blah, blah. Well, I guess we're going to stop at the second order partials. You don't need to do this in general for, in different variables. I think it would be fine to do it for just, let's say, 3 variables, right? So that the numbers don't get out of hand. I mean, these matrices can get big otherwise, right? But I think you'll notice the pattern. I think if you confirm for yourself that this formula works for 3, functions of 3 variables, you'll see the pattern. I think you'll be pretty comfortably persuaded it'll work for any value. Okay, so that's all I'm going to say about 4.1. Everything else is either, again, review of single variable stuff or pretty much what I just told you right there. So I'm going to move on now to 4.2. So 4.2 is where we start optimization. Optimization in single variable, again, hopefully is all familiar. Let me remind you the very, very quick how do you do single variable optimization is this right here. The big idea underneath it all is these three conditions. If you find a point that's in the interior of your interval where the function f is differentiable and if the derivative is not 0, all three of those now, this is, all three conditions satisfied, it immediately follows that there's no way that this could possibly be a maximizer of your function. And it's a pretty easy observation. Take, for example, a point like this right there. This is in the interior of my interval. You can't exactly determine differentiability from a picture, but as is vaguely suggested here, if this function is differentiable at that point, and the derivative you can see, assuming it's differentiable, does appear to be non-zero, right? This is obviously not the maximum value of the function because the function is getting bigger as you move, as you might call uphill there on the graph. If the function's still getting bigger, you're not yet at the top. Right? Everybody happy with that? All right, so I color this in green because this is what I'm going to call good news. Seems weird to say good news when the punchline was that we did not find what we were looking for. The good news is that I was able to draw a conclusion at all about what's happening at this point. Okay? And here's more good news. Most of the points in the domain will satisfy all three of these conditions, and again, we get to draw conclusions, and namely that these are not maximizers. So let me just highlight to be clear, all of these points, all of those points, all of those points, and all of these points. At all those points, all three of those conditions are satisfied. We know something, namely that these are not the points we're looking for. Okay, so what we have to turn our attention to now is what happens when any one of these three conditions fails. And there's different ways that could happen. A point in my domain could fail to be in the interior if it's on the boundary. Right, and I've got a couple of those. Here's a boundary point. Here's a boundary point. Okay, well, my condition's not satisfied. I don't have to admit I don't really know for sure what's going on at those points. I could probably make some sort of other argument at a later date about how to deal with that. But for the moment, based on this elimination argument, I don't know. Likewise, a function could fail to be differentiable at some point, such as here. Right, this point right there, the function's got a little corner. I can't use a derivative argument to draw conclusions about this point because there is no derivative. The value of the derivative, if it were differentiable, the value of the derivative could fail to be not 0. In other words, the derivative could be 0. And that happens too, right? So that's the case at that point and at that point. And at these 2 points where the derivative is 0, look, I can't just, based only on looking at the derivative, the function's not increasing in either direction. So again, I can't really draw a conclusion. Okay. So if either of these three things happen, so these are ors right here, right? So if any one or more of these conditions happens, my elimination argument crashes and burns. I have no idea what's going on at that point, at least not from this point of view of this elimination argument, and I have to throw up my hands and say, I don't know, I'll deal with it later. I'll figure out something at some point, but I'm going to have to take a careful look at those points. So we call them critical points which I think is a little bit of a cop-out. It kind of makes it sound like I've drawn some conclusion. I think exactly the opposite is true. When any one of these red conditions is satisfied, the reality is that I don't know what's happening at those points. Not that I do know. Okay, so notice not all of these red points are maxes or mins. Right? There's several that obviously aren't, such as this one right here. So, again, no conclusions. Okay, this is all review. This is all old news. I hope this all makes sense. Now, the main reason I show you that is because of how analogous the multivariable version is. The multivariable version, again, starts with an elimination argument. These three conditions right here. If you're in the interior, by the way, let's look at this point right here. That point would appear to be in the interior of our domain. Function, again, you can't infer from the graph, but let's suppose that the function's differentiable here, and as would seem to be vaguely suggested by the picture here, let's suppose the gradient is non-zero. Well, this couldn't possibly be a maximizer. I get to draw a conclusion. I know something. I know about that point. That point is not what I'm looking for. Right? And again, morally equivalent argument. Does that make sense to everybody? I mean, the gradient's non-zero. That means the function's increasing if I go in the direction of the gradient. So just go in the direction of the gradient. I'm in the interior. I could definitely go that direction. Whatever direction that is, this is not a maximum. Okay. So again, I have to wonder what happens when one of these conditions fails. Suppose, for example, that I have a point that fails to be in the interior, namely a boundary point, such as maybe this one, or this one, or frankly any of these, right? All those boundary points. I know, man, if I'm on the boundary, what if the gradient tells me to go that way? I can't go that way. My argument just doesn't work, and I can't really quite fix it, at least not, conveniently, generally. So my argument fails. I have to call those critical points. What if a function fails to be differentiable? Well, again, I can't make any arguments about what the gradient means. The function's not even differentiable. There might not be a gradient. What if the gradient fails to be not zero? In other words, what if the gradient is zero? Then there's no direction that the gradient points. Right? So various of these points, so for example here the gradient's equal to 0. It's kind of flat, if you will, at that point right there. It's kind of a pass, kind of a mountain pass sort of a thing. The function fails to be differentiable there. The gradient is 0 there. Gradient is 0 there. And of course I have boundary points sort of a lot of other places. So these red points, I know nothing. Now everywhere else I'm good. And all the rest of the points in the domain here, yeah, I can eliminate all of these. And all that remains, excuse me, typically a small number of points in the interior. And then there's the little matter of the boundary, and we'll talk later about how to deal with the boundary. Okay, so at these red points are where, if there is a maximizer, it's going to have to be one of these, but where did I get these red points from? I got them from the fact that, whoopsie, wrong color, from the fact that I don't know what's going on at those points. I was not able to draw any conclusions. So again, we throw up our hands, we call them critical points to make it sound like we learned something. When in fact, these are just the points where I don't know how to deal with it. Okay, and so look at the analogy again, really strong analogy between the single variable strategy, the multivariable strategy. They're practically identical. Everybody buy it? Okay. And coincidentally, Christmas colors. How about that? All right. So let's see here. We'll see an example here. Yeah. Sorry, I missed one thing. Let's look at terminology just a little bit. A point like this, where it kind of curves downward, maybe in that direction, but maybe curves upward, kind of in this direction. So I like to think of a Pringle, right? They call that a saddle point because they hadn't invented Pringles as of when this came out, right? I feel like they would have called it a Pringle point otherwise. Anyway, the term stuck, so we call these saddle points. If I can get this thing to move. Be aware as well, though, there are other kinds of saddles. There are lots of weird-shaped saddles. The three-dimensional, well, let's say it this way. A two-dimensional domain, there's a lot more room to move. There's a lot more directions in which functions can be weird. There's anomalies and oddities in multivariable functions that just don't have analogs in single variable. So the term saddle is a catch-all referring to all of these kinds of points where it is neither a local max nor a local min. And for fun, I'd encourage you to image search monkey saddle for two reasons. For one thing, it's a pretty wacky surface called a monkey saddle, where like a regular saddle slopes downward where your left leg needs to hang down, and downward where your right leg needs to hang down, but then upward in front and back. A monkey saddle hangs downward in two forward directions and in one backwards direction for the monkey tail, right? Adorable, right? And then upward in three different directions to kind of separate those from each other. So it's a really interesting picture, and again, there is no single variable version of that. They also have all sorts of other wacky kinds of shapes that can happen. Okay, so example. So here is a function, and let's find the critical points. So we're just going to go through and look at the three different conditions. There's three different ways to get critical points after all. Boundary points. Are there any points in the boundary of the domain for this function? Well, this function's defined everywhere. It's a polynomial. It's defined everywhere. There's no... All of R2 is the domain. It has no boundary. So there are no boundary points, and we get no critical points. Okay, continuing the search. What about differentiability? Any point where the differentiability fails would have to be a critical point. That's a polynomial. Polynomials are differentiable everywhere. Old fact from chapter 2. Freebie. Right? So this is differentiable everywhere. So again, there are no critical points that we find from that condition. All right, fine. Okay, lastly, we look for where the gradient is equal to 0. So we compute the gradient. We set it equal to 0. And we look for points that satisfy this little resulting system of equations. And this little system of equations is actually pretty easy to solve. In this case, this equation tells you x has to be plus or minus 1, and this equation tells you y has to be 0, and so altogether we have these two critical points right there. Everybody good? Excuse me. Yeah.
Can you explain one again, how they're all on the interior?
Yeah, so the point is the domain for this, if I wanted to be more careful and proper about this, I should have said f is defined as a function from R2 to R1. Okay. But the implication here is that, when you have a function written down and there's no suggestion as to what the domain is, the implication is the domain is the largest possible domain. It's defined everywhere it's defined, that kind of thing. So yeah, it's defined on all of R2. Okay. Yeah. Okay, now, we got lucky. In this example, this system was easy to solve. X only appears in the first equation, y only appears in the second equation. None of the equations are linked together or anything like that. It's just an easy equation to solve. You will not always get so lucky. Here is a little system of equations that's significantly harder to solve. And I just kind of want to show you how this breaks down, so you'll kind of, if you encounter something like this, you sort of know how to proceed. You look at this first equation right here, And that pretty immediately tells you x squared is y squared. But there's two different ways that x squared can equal to y squared. It could be either one of these. Right now, a lot of high schools will let you get away with being extremely sloppy on this and just kind of canceling the squares. That is absolutely not legal. And it's also not, it's not good enough for our purposes, right? So what we're going to have to do is be careful with that kind of thing. Specifically, we're going to have to consider these two as separate cases. We'll deal with them separately. Each of them is going to contribute to our collection of critical points. So let's start with case 1. If x is equal to y, you can plug that into this second equation. The second equation becomes this. And you can solve for y. No big deal there, just quadratic. And y has to be 0 or -1, which is not a point. But with this formula for y, which we then plug back into our case here, x equals y, from that I can then conclude the x's and therefore have our critical points. Everybody with me? And that was all just case 1. Now, just as important, equally important, is case 2. X could totally equal to -1, just as easily. So making that assumption, plugging that into our second equation, our second equation becomes this. Different equation for y. I get different values of y. Okay. And furthermore, not only do I get different values of y, but these values of y I plug back into, now of course, my different case. I'm going to plug into x equals -y because that's what led to these values of y in the first place. Right? And that then gives you, again, another couple of critical points, like so. Everybody see how that works? So altogether you have 3. Now it kind of looks like 4, but of course these are the same. Right? So in actuality you have 3 critical points. And if you hadn't been careful with the cases, you only would have found 2 of them. Okay. Now, quick point of philosophy. You all heard me say this a million times. I think this being the last lecture, it's probably one of the last times you're going to hear me say this, but it's of course about ideas and reasoning, not answers. If it should happen to work out that the maximizer you were looking for happened to be one of the critical points that you did happen to find, but if you didn't consider the cases and you absolutely completely ignored the third critical point, the fact that the critical point that we wanted happened to be one of the ones you found is a coincidence and doesn't mean anything. And the point is the reasoning still has a problem, right? So keeping in mind that exams are graded on the basis of your reasoning, not on whether you got the numerical answer, this kind of an issue is important no matter what, even if the critical point in question is kind of already on the page somewhere else. Does that make sense to everybody? Again, we're always going to be looking at the reasoning. All right. Okay. Moving along. So how do you classify critical points? Well, we have a second derivative test. It's a lot like the single variable second derivative test. I'm going to give you a quick point of view on that single variable second derivative test. Comes from the Taylor series, or more to the point, the Taylor polynomial. This is the degree 2 Taylor polynomial. If you're looking at a critical point and trying to figure out what to do with it, well, if the derivative is 0, this whole term goes away. And the entire behavior, at the critical point, the entire behavior of the function is determined by the second order term. And this is actually pretty easy to analyze because 1/2 is always positive, and x minus a quantity squared is always positive, right? And so this second derivative tells the story. If the second derivative is positive, that means that this whole term is always positive, which means the function is increasing in all directions, which would mean that you have a minimum. And likewise, if this second derivative is negative, then this is always negative, which means it's like this, which means you're at a maximum. Okay, so that's a point of view on the single variable second derivative test. Now there are other points of view. This is the one I want. So what we're going to do now is try to apply that same idea here for the multivariable second order Taylor polynomial. Again, we're going to consider what happens when the derivative is 0, and thus that we're at a critical point, and so this term goes away. The entire behavior of this Taylor polynomial is determined by this second order term. I need to know, when is this second order term always positive? Or when is it always negative? And don't forget, it's a quadratic form. So really, what I need to decide is under what circumstances is this quadratic form positive definite, or negative definite, or indefinite. And I'm sure you all remember those terms from Math219, linear algebra, right? Well, it's a long time ago probably by this point. But anyway, analogous reasoning, positive definite would mean you have a minimum, negative definite would mean you have a maximum, indefinite would mean that you have a saddle. So the analogy is quite strong with the single variable version. Here's where it breaks down how to decide if this quadratic form is positive definite, negative definite, or indefinite. That's a whole thing. There's this whole process of you got to look at your matrix, and various different things you have to check. Right? It's kind of inconvenient. So there is some clever linear algebra that you can do. I've hit the highlights right here. You can look at that if you like. You're not required. This is not. You're not going to be tested on this bit. But if you're curious, how does the linear algebra kick in here and streamline these questions? It turns out, as a nice punchline, that this is what you get. And this is called the second derivative test, multivariable second derivative test. It starts by looking at the determinant, weirdly, the determinant of your Hessian matrix. Kind of weird. If it is positive, then you have to ask other questions. If it's negative, you have a saddle point. There's a nice, crisp, convenient ending to that little story. Negative Hessian determinant always means saddle point of some description. Monkey saddle, human saddle, whatever. There's definitely a saddle of some sort. And it's also possible that determinant could be 0, and this is one of the cases in which the test fails, and you learn nothing. So it's not. A lot of people misunderstand this and think that if the determinant is 0, then this means that it's definitely not a maximum and definitely not a minimum. Absolutely not. Right? It's that the test fails to draw any conclusion at all. So be careful with that. Yeah.
What would the graph around the point look like if the determinant was 0?
It'd look like a saddle point, like so. So let me, I can go back up to where we have a picture. Whoops. Here it is. Yeah, it would look something kind of like this, where kind of like a Pringle, right? Where it's going to be kind of downward in one direction and kind of upward in the other direction. Yeah. And why that is the case is a long story in linear algebra. Yeah, that's not this course, right?
So for some saddle points, you get a negative determinant, and for some, you get a 0 determinant?
Yes, that's true, because that's right. Because if it's a 0, if your determinant is 0, then it could be a saddle, but it could be something else. And so, yep, right. Okay. All right. So let's put this into practice here. Oh, I'm sorry. I didn't finish the story here. If the determinant is positive, you have to look at more information. The second step of that process is to look not at the whole matrix, but to look at the top top left element of the matrix, the XX second partial. And here we get something that actually is kind of a single variable analogous. Positive means minimum, and negative means maximum. So y'all will recognize that in the single variable case. So that's kind of convenient. But this only kicks in. This is only relevant if the determinant of the Hessian is positive. Okay. All right. So plug and chug. We've already found for this function that we have these two critical points. We didn't know what to do with them. We just kind of said, I don't know, I'll deal with them later. So let's deal with them. Looking at this first point here, plug it in, see what your Hessian determinant is, and it is negative, which tells me saddle point. It's as easy as that. Plugging and chugging, right? Just following the procedure, following the little algorithm of the second derivative test. Cool. Let's look at the other one here. Let's see this point B, 1, 0. Plug that into your Hessian determinant. It's positive. Like here, that alone doesn't really tell you anything other than that I can proceed here because it's positive to looking at fxx. And fxx, I need to know if that's positive or negative. Well, fxx, I can see right there, and it is 6, which is positive. And that tells me local min. Again, just following the table. Everybody see how that works? Real pluggy chuggy. Excuse me. Okay, so here's a next question. I'm going to ask. So we've got this process of elimination game that we're playing. We eliminate most of the points in the domain. We look at what remains. Seems like whichever point gives the biggest value to the function of those that remain has to be the maximizer. It's very tempting. Here's a subtle problem with that reasoning. Processes of elimination only work if you know that the thing that you're looking for exists. Right? So, you ever played 3-card Monte? You know what I'm talking about. Here's an analog. Let's suppose that I want to figure out who in this room has been to the moon. And I ask everybody except for him. And nobody's been to the moon. Does it follow that you've been to the moon? No, of course not. Right? You haven't been to the moon. Okay, yeah, gotcha. So, doesn't follow is the point, right? So, we have to watch out for that nonsense here. If I eliminate most of the points and I want to draw conclusions about the ones that remain, I need to know that this maximizer I'm in search of actually exists. And there's several ways that a maximizer could fail to exist. Look at what's going on over here at the sort of the left side of this interval. Because the interval over here is open, there is no endpoint there. My function can just keep getting bigger and bigger and bigger and bigger and bigger as I approach this non-existent endpoint, right? This function has no maximum value. It does not achieve a maximum value anywhere because there is no maximum value. So process of elimination wouldn't work there. Analogously, if you're sort of unbounded, well, the function can just keep getting bigger and bigger. Or if your function is allowed to have a discontinuity in it, if you're allowed a discontinuity, well, then you could just approach infinity right in the middle of your interval. Right? And again, no maximum value. So what we need to do is to figure out how to eliminate these possibilities. If your domain is closed, in other words, if it contains all of its boundary points, in other words, if that nonsense doesn't happen, if your domain is bounded, namely if you can put it in a box, if it doesn't extend infinitely in any direction, in other words, none of this nonsense, right? And likewise, if your function is continuous. In other words, none of this nonsense. It turns out that these three conditions, in other words, eliminating these possibilities, it turns out that's enough to conclude that yes, indeed, there is a global maximum value. So this trio implies that there is a global max, and if you know there's a global max, then you can find it by process of elimination. All right, now we're going to skip this next sort of page and a half, I guess it is. What we have here is a discussion of how to check the boundary. Remember, our methods so far don't apply on the boundary. Right? Boundary points are critical points. We can't eliminate them with our existing arguments. So how do I eliminate boundary points? What I'm showing you here is what I would call a blunt, naive, brute force, tedious approach that we really wish we had a better alternative to. And so rather than go through all of this inconvenience and pain, right, let me just show you instead the much easier way to do it. Right? This is the much easier way that we sort of wished we would have had. Okay, so this is called constrained optimization, sometimes called the method of Lagrange multipliers. I'm going to start with a quick example. Find the point on this curve closest to the origin. This is what we call a constrained optimization problem because it is not as simple as I want to maximize or minimize distance from the origin. If I ask the much simpler question, hey, what point is closest to the origin? The answer is easy. 0. The origin is the point closest to the origin. Nothing to it. Right? What makes this problem hard is the constraint. I am not allowed to just look at any point in the domain I want. I'm only allowed to look at points that satisfy an algebraic condition. Right? This makes the problem quite a bit harder. It turns out that there are lots of such questions, and they are important, and we are going to develop some lingo to talk about this. There's always going to be a function that I want to minimize or maximize. We're going to call this the objective function. And there is another function one of whose level sets describes the constraint. And we're going to call this, in this case, our constraint function. So a constrained optimization problem, there are two functions involved. There's the one that is the objective, and then there's the one that's the constraint. Make sure not to conflate these. I see now that I'm out of time. I've already sent y'all an email indicating that I'm going to send you a recording. We'll talk through the rest of this stuff. It is very algorithmic. That's the good news. And I'll have that recording to y'all in the next couple hours. Okay, see y'all later. Have a good one. Make sure I get you marked down for attendance.
Are you going to send us information about the final?